Alright, Math 152, Module 2, Chapter 3, Probability. So we're going to start talking about how do we get those numbers that we hear and the decimals and the percentages. And what does it mean? Alright, 3.1, Basic Concepts of Probability and Counting. So probability experiment is an action or trial through which results are obtained. Specific results are obtained. We're trying to figure out, what is it we're trying to get. So the result of a single trial in a probability experiment is an outcome. And it's things that are in parentheses, these are my words. So what happened? So the outcome is what happened. What happened when you rolled that dice, or picked that card, or picked that marble. The set of all possible outcomes of a probability experiment is called a sample space. So we have to consider what outcomes can we have? Is it possible to get the outcome that we're looking for? And then an event is a subset of the sample space. So what are you looking for? So an outcome is what actually happened. Sample space is what can happen. And an event is what you're looking for specifically. Am I looking for a 3? Am I looking for a 5? Am I looking for a 7? What am I looking for? And then what happened? And then what can happen? And we need to know those so we can actually calculate our probabilities correctly. Alright, so we're going to identify the sample space and determine the number of outcomes. So survey consists of asking people for their blood types, O, A, B, and AB, including whether their RH is positive or negative. Determine the number of outcomes and identify the sample space. So we're going to first do what we call a tree diagram. And the tree diagram will always put together what are your possibilities so you can see them all together. Now many times you won't need to do this, but if you just need to do this because of the way you're calculating your answers, this is a good way to actually do this. Do your look at your possibilities. So we have O, A, B, and AB here. And then whether they're positive or negative. So this can be positive or negative. Positive or negative. Positive, negative. Positive or negative. So see how we created a tree. And from this tree, we can create our sample space. Our sample space, normally we put it in these braces. So what combination of possibilities do we have? So what can happen? We can have O positive, O negative, A positive, A negative, B positive, B negative, AB positive, AB negative. So that's how you can use that diagram tree to figure out all of your possibilities. So what happened? If we flip a coin 3 times, what are all our possibilities of what happened? If we're trying to figure out the blood types, what are all our possibilities? So nothing else can happen outside this. I can't have a C positive. I can't have a D negative. Because these are all my possibilities. This is my sample space. So how many outcomes did we actually have? And this is important because this is going to be our denominator a little later. All of our possible outcomes. How many ways do we actually get our event? So this is 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 outcomes. And how many ways can I get the one outcome that I'm looking for? So it's possible outcomes. I'm going to look for a specific outcome a little later. Alright, there we go. Alright, a simple event is an event that consists of a single outcome, meaning there's only one way we can get that outcome. Tossing heads and rolling a 3. So if I have a coin and I have a die, there's only one way I can get heads and 3. But an event that consists of more than one outcome is not simple. So that looks like tossing a heads and rolling an even number. So if I have a die, my even numbers are 2, 4, 6. So these are all the possible ways that I can actually have an outcome that looks like this. So simple outcome means there's only one possibility, that's it. Not simple means there's more than one way to get your outcome. So, and we just think about that so that way when we're looking at all of our possible outcomes, we want to look to see if there's more than one way to get the outcome that you're looking for. Because if there's more than one way, then we have to calculate that and or add that or include that into our calculations. Alright, the fundamental counting principle, we'll use this a lot in statistics. The fundamental counting principle is if one event can occur in n ways and a second event can occur in n ways, the number of ways the two events can occur in sequence is m times n. And this can be extended to any number of events in sequence. So we can roll a die, flip a coin, and pick a card. We can do all of that. And then we'll multiply all those possibilities. So let's look at how we could have calculated our number of outcomes as opposed to actually doing the diagram tree. So survey consists of asking people for their blood types, O, A, B, and AB, including whether they are Rh positive or Rh negative. So there's 4 letters, and then there's positive and negative, 8 outcomes. So we multiply the possibilities of letters, possibilities of the sign, multiply them. So that's the quick way to get your number of outcomes that you can calculate your probabilities. Alright, so let's look at another way. The access code for a car security system consists of 4 digits. Each digit can be any number from 0 to 9. Alright, so these are going to be independent problems, meaning that it's not going to be building upon each problem. The problems that we have below, they're one problem. So they're one problem each. So that one doesn't depend on the other. Alright, so each digit can be any number from 0 to 9. So we use the fundamental counting principle. How many possibilities do we have for the first digit, second digit, third digit, fourth digit? So if we look at all of our digits are 0 through 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So there are 10 digits. There are 10 digits. 10 possibilities here, 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 and here. But let's look when they actually put restrictions on our fundamental counting principles and when they don't. So how many access codes are possible? We have these 4 digits. When each digit can only be used once and not repeated. So once I use 0, I can't use it anymore. Once I use 1, I can't use it anymore. So I want to look at each digit to see what my possibility is. So the first digit, let's think about it. I don't have any restrictions, so I can use all 10 digits. But my next one does have a restriction. Whatever I have here, I can't use it anymore. So I'm down to 9 numbers now for my second digit. Whatever I have here, whatever numbers are used already, I can't use them. So I'm down to 8 digits. And the last, what do you think it is? 7. So I had all 10, and then I had to take one away because I already used that one. I have 9. I had to take 2 away because I've already used them. Like, I left me with 8, and then I already used 3, so left me with 7. So 10 times 9 times 7. Times 8, sorry. 10 times 9 times 8 times 7. So that means that's 5,040 codes that are possible. Alright, next. Each digit can be repeated, but I don't have any restrictions. I just need a code. So if that's the case, 10 digits can be used first. Second, I can use all my digits still. I can still use all my digits. I can still use all my digits. So notice I'm doing them individually. I'm not looking at them as a whole. I'm looking at each individual number. And what does that equal? Mm-hmm. 10,000 codes, 10,000 possibilities. But I have no restrictions. So when I have a few restrictions, it decreases. When I have no restrictions, I have all my possibilities. It's kind of like I'm using my whole entire population any kind of way I want. And the last one, each digit can be repeated, but the first digit cannot be 0 or 1. So it's I can repeat them, but the first one only has a restriction. So if that's the case, I can't have this or this. So what are my possibilities? I can't have 0, can't have 1. 2, 3, 4, 5, 6, 7, 8, 9. Make sure everybody's got that. So 0 through 9 are all my possibilities. But they told me I can't use 0 and I can't use 1. So what do I have left? 2, 3, 4, 5, 6, 7, 8, 9. So those are 8 numbers. So remember, you want to count how many possibilities you have. You want to count how many possibilities you have. Just move my table. So I can't use 0 or 1. So I have 8 possibilities. They could have changed this problem and said each can be repeated, but the first digit must be 0 or 1. If it must be 0 or 1, then I only have 2 possibilities here. So if it must be 0 or 1, it's 2 possibilities. If it cannot be 0 or 1, we have the opposite of that, which is 8 possibilities. And then the other numbers, there were no restrictions. So for the second digit, the third digit, the fourth digit, there was no restrictions. There are no restrictions. Good, that is 8,000 codes. Good. So be careful with these and the wording, and make sure you understand what they're asking you for. If there are restrictions or if there aren't restrictions. So aren't restrictions, it could be that they didn't want to use 0 because it looks like a letter O. Or if you're mixing numbers and letters, they may take away the letter O in the alphabet, which is 26 letters, and the number 0 because you might get it mixed up. There are 10 digits, so you might take both of those away. So look at all the possible ways. Okay. All right, the types of probabilities. The method you will use to calculate a probability depends on the type of probability. All right, and we're going to round to 3 decimal places. So in this section, it's going to be customary, if they don't tell you, to round to 3 decimal places. So if they do not tell you or they don't give you any kind of guidance, we're going to round to 3 decimal places. So the first type of probability we're going to be working with is called the classical, or sometimes they'll call it theoretical probability. Each outcome in a sample space is equally likely to happen. I call this a la-la land probability. I call it a la-la land because this is what happens in a perfect world. In a perfect world, if I roll a 6-sided die 6 times, I'll get 1 the first time, 2 the second time, 3 the third time, and so forth. So in a perfect world, this is what would happen. So la-la land probability. And how do you calculate that? The number of outcomes in events E over the number of outcomes in the sample space. So we're looking at what happened, or what are possibilities of that outcome in that event, and then what can happen altogether. Let's look at our first example. I have a lot of space here for this first one because I want to break it down. You don't have to do all the space. I'm just showing you so you can see what happens. Alright, so you roll a 6-sided die, find the probability of each event. So I'm going to write the sample space so I can show you just exactly what we're working with. Okay, so you don't have to do this. showing you so you can see what we're working with and how this actually works. Our event A is rolling a 3. This is a simple event because there's only one way I can get a 3 here. So simple event means I have a 1 on top. That's the only way I can roll a 3. But then how many ways can I roll, period? 6. I'm going to get my calculator out real quick to show you this one. So 1 divided by 6. This is a repeating decimal, but we don't want the bar on top. We want to round to 3 decimal places. So 1, 2, 3. So the 6 is going to become a 7 because of that 6. If you need some rounding rule tips, let me know. I'll send some to you. Okay. Event B is rolling a 7. So let me look at all my possibilities. How can I roll a 7? I can't. So there is such thing as not likely to happen or will not happen. It's not possible. So you can have a probability of 0. Okay? So don't count it out. Alright, event C is rolling a number less than 3. So here's what I kind of think about the wording. Rolling a number less than 5, excuse me. I got 3. Rolling a number less than 5. So I'm looking at all my numbers that are less than 5. Not less than or equal to 5, but less than 5. So I have 1, 2, 3, 4. So I have 1, 2, 3, 4 numbers that are less than 5. Notice how my denominator is the same for all my possibilities. That's because in La La Land, your denominator will not change because it's naturally there. There's 6 sides to a standard die. Some die have 6, 10, 12, 20. There are 52 cards in a deck. That number does not change. We can't change it. There's 12 months in a year. So that's naturally the number. So we can't change it. So 4 divided by 6. Hopefully you can calculate it. 0.667. Next type of probability is empirical or statistical. Statistical probability. This is based on observations obtained from probability experiments. This is reality. This is what really happened. So I roll my die 6 times. I'm supposed to get 1 the first time, 2 the second time, 3 the third time. But what really happened, that's empirical or statistical. Statistics is what was the data collected. Okay? So for experiment, this is used for experiments repeated many times. So we're rolling that die a whole lot of times. This is also considered relative frequency of an event. So we talked about relative frequency in 2.1. It pops up again here, but just as a different face. So empirical probability is the same as relative frequency. You're going to take the frequency of the event instead of the class, divided by total frequency. So empirical probability is the same as relative frequency. And we're going to see relative frequency, I think, 2 more times. It's going to have a different face or different name, but it's really going to be relative frequency. Alright, so let's look. A research organization is conducting a survey of randomly selected U.S. adults to determine how they read books during the past year, how they read books during the past year, if at all. So far, 1,502 adults have been surveyed. The pie chart shows the results. Note that digital books include ebooks as well as audiobooks. What's the probability that the next adult surveyed read only print books during the last year? Okay, so we're using empirical probability to predict what will be picked next. All right, so here is our graph. And they wanted to know read-only print books. Read-only print books. So this is what we're looking at. Read-only print books. So we have to determine what is our probability. So 560 read print books. Out of how many? What is our total frequency? Lucky us, they did give us the total up front. I don't know if you saw that. See? Lucky us, they gave it to us. But if they did not give us the total frequency, we could just add all of our frequencies together to get that number. So I'm going to pause and add all these together. Gives you that 1502. Okay? Yep. So they don't give you the total. They were nice to us and gave it to us. They don't just add all your frequencies or your possibilities, whether it's in this form or chart. Just add them all together so you can get that bottom number. So according to the formula, is F over N, but we have our frequency over our total frequency, which is the same thing as AN. So what is 560 divided by 1502? 0.373. Good. 0.373. Let me talk about law of large numbers real quick, because we'll see this a lot. I mean, we'll use it a lot, I'll say, and I'll refer to it a lot. So law of large numbers just states, as an experiment is repeated over and over, the empirical probability of an event approaches the theoretical probability of an event. So remember, we're talking about what supposed to happen and what really happened. So as we repeat an experiment or an event over and over again, our empirical probability will get closer and closer to our theoretical probability. So if I flip a coin 10 times, it's supposed to get half and half. I might get 6 and 4. But if I do it 1,000 times, I might start getting like 490 to 510. So it'll get closer and closer to each other the more you do that experiment. Alright, and the last is subjective probability. This is actually a probability. I know it's going to be crazy once I explain it. So you're going to use your intuition, an educated guess, or estimates. So a doctor may feel a patient has a 90% chance of full recovery from a surgery. Well, how are they getting that number? Where are they getting it from? They're just guessing. Unfortunately, they're just guessing. So there are instances where you have an educated guess or estimate of what you think will happen. Alright, so classify the statement as an example of classical probability, empirical probability, or subjective probability, and explain your reasoning. According to company records, the probability that an automobile will need covered repairs during its 3-year warranty period is 0.46. So we want to know, is this something that naturally happens? Meaning it's going to happen every single time. That is theoretical, or that is classical probability. It's going to happen because that number cannot change. Is this a empirical rule, meaning we had to do it over and over and over and over and over again to get this, or we had to take some data to get this? Or is this just a good guess? It's just the best guess that I have. It's just what I think, as opposed to I don't have any data that goes behind it. So just think about this. Is this number consistent? Is it going to happen every single time? No matter what? No, it's not, because we don't have any data to back up that this is going to happen every single time. this looks like this happened over and over and over again. Like they looked at something over and over again. Like they had some data and they pulled it. So this, according to company records, this means that some data was used. So empirical is when data is used. Something was repeated. You had to do some work. So empirical is something was repeated. You had to do some work. Data was collected somewhere. So for B, let's look at B. The probability of choosing 5 numbers from 1 to 40 that match the 6 numbers drawn by a state lottery is 1 over 40 times 40 times 40 times 40 times 40 times 40 equals to this 1 over 3,838,380. And then this is a decimal that goes with it. So let's think about it. Is this what happens naturally every single time? Like we can't change this. This is what happens every single time. And we're not doing any work. Is this something happening over and over and over again and we pull this from data? Or is this a good guess? You said classical, you are correct. They only use 1 through 40 in the lottery. They don't use 1 through 36. It doesn't change. It's always the same thing. And there was no work. There was no data collected. This is just what happens naturally. So because only 1 to 40 is used consistently. Like it's always the same numbers. Like the state lottery, they do not change those numbers. It's always going to be the same thing. And they didn't do any work. They're just thinking about what those numbers are, about what will happen. Alright, and the last, an analyst feels the probability of a team winning an upcoming game is 60%. Analyst feels. So we already know there ain't no data behind this. This is strictly off of feeling. No numbers, no data, nothing naturally. So this is subjective. Feelings were used. I can't look at what happened last time. I can't happen at what happened in the last game. I can't look at what happened last year. I can't look at what happened yesterday. There's nothing I can do to get that number 60. And an analyst just went off of a feeling. Okay, so that's subjective. Alright, range of probabilities rule. The probability of event E is between 0 and 1 inclusive. So these are the only numbers that we can have as a possible answer. So probability has to be a decimal. It'll be from 0.000 or to 1.000 and anything in between. I know Maury said, I'm 1,000% sure that's the baby daddy. No, you can't be 1,000%. Can't be. Now we're talking about like businesses. Now you can't go over 100% because you can make profit. But we're talking about the probability of something happening. Just 0 to 1, and you can change this to a percentage. But normally we keep it in decimal form because this is easier to work with as far as that's concerned. So if you're interpreting, you may want to change it to a percentage, but we're going to keep it in decimal form, and we want 3 decimal places just in general. Alright, when the probability of an event is 1, the event is certain to occur, like it's going to occur. When the probability is 0, the event is impossible. An event that occurs with a probability of 0.05 or less is typically considered unusual. typically considered unusual. So less than 0.05, not 0.5, but less than 0.05 is considered unusual. So first we have the 2 standard deviations away from the mean. Now we have the probability of 0.05 or less is typically considered unusual. Okay? Complement of event E. The set of all outcomes in a sample space that are not included in event E are denoted by E prime. And so if we think about it, the event happening plus the event not happening is 1. So we're talking about what we're looking for and what we're not looking for. All of that is included in 1. So if we want to look at all the possibilities of something not happening, we're just going to take the opposite of what we do have. So they're complements. What we do have, what we don't want. I don't use complements a lot, but some people can look at them instantly and just go and just go. Me, it takes a little while to get there. But let me show you what that means. So find the probability of randomly selecting a social networking site user who is not 25 to 34. Not 25 to 34. So this is what we're talking about. Not this. Not 25 to 34. So for that probability, you want everything but this. So we would do 1 minus that frequency divided by, thankfully they were so nice, they gave us a total frequency. We didn't have to add them all together. But by total frequency. So 1 minus, they want not, so not 25 to 34. They want this, and that. They don't want that. So this, and this. So you can put that in the calculator. I like to put fractions in the calculator with parentheses, but there is a fraction button in some of your calculators. I don't remember where it is. I think it's under math. Okay. Ooh, so you can't see that. So I put it in parentheses. So 0.745 is our answer. Now this is how I did the problem. You don't have to do it this way. This is how I do the problems, and I still get my right answer. So if you don't get the complement, just go the old school. What would you do? So I added all those numbers that I wanted. 84, 459, 546, 432, 369, 345. I added all those together. I know it took me a little while to do that. But I added all those together. I didn't do my 1 minus. I want to add them together real quick. And guess what? Still got the same answer. So complement, you don't always have to use it. You can use it if you can quickly see it. And some of you all are really good at that. You can really quickly see it. But for those of us in my corner, you can do either one. You just add the ones that you want and leave out what you don't need.